Video number 3, which is lesson number 4 in chapter 5, we're going to be talking about this thing called the general multiplication rule. We've kind of talked about this in the past, especially in the second video when we covered probability models, that in order to do multiple tasks in various numbers of way, how to determine the total number of outcomes possible is just to multiply them, and that is what is called the multiplication rule. In the second video, we talked about what if you wanted to have 3 kids? How many different possible combinations are there? And each kid, you have 2 outcomes, and so there were 8 outcomes, which ends up being really the same exact thing as our coin example here. Because each time you flip a coin, there's only 2 outcomes. And we're going to flip it 3 times. So this is, the first flip, second flip, third flip, and we have 2 times 2 times 2, which is 2 cubed, which is 8 different ways of accomplishing that. Now we could talk about zip codes, we'll say. Zip codes use numbers from 0 through 9. How many different 5-digit zip codes are there? Now zip codes can begin with zeros, so there's 10 possible numbers that could begin the first digit of a zip code. And we can repeat numbers in a zip code, because if you think of our zip code, the second and the third numbers are repeats. So really, each of our 5 digits in a zip code can be repeated. And so if we multiply all of those things, 10 times 10 times 10 times 10 times 10 is 10 to the 5th, which is, there are 100,000 different possible zip codes, which means there can be 100,000 different cities. So what if we go beyond 100,000 cities? Then what do we do for a zip code for that 101,000th city? Well, then we need to start breaking out 6-digit zip codes, and so forth and so on. Now, in addition to getting the 8 outcomes here for flipping a coin 3 times, we're going to create something that we could use to calculate probability if we wanted to. It's not an entirely necessary thing, but it's definitely possible. And it's called a tree diagram, which I'm sure you guys have seen before, and we're going to do more on today. So a tree diagram to show the sample space. We're going to say here's where everything began. And from where everything began, we have 2 outcomes. We have heads and we have tails. Well, let's say the first time we tossed the coin, we got a heads. And then the second toss could either end up heads or tails. And then let's say that second toss was a heads, so we go to flip the coin the third time, and we're going to get either a heads or tails. Well, now what we have to do is go back and say, all right, well, what if in that second flip where we had a heads, what if it was a tail? Well, if we flipped a tail and then we go for a third flip, we can get a heads or tails. And then we got to go all the way back to this beginning case. What if the first flip we did was a tail? Well, then the second flip could be heads or tails. And then off each one of these combinations is a heads or tail. Okay, and then here's your 8 possibilities. You could flip a heads, heads, heads. We could flip a heads, heads, tails. We could flip a heads, tails, heads. We could flip a heads, tails, tails. And then I could do the same thing down here for the other 4 combinations. 1, 2, 3, 4. So there are 8 possibilities here. And if I wanted to, I could write out what the ending of all of those branches ended up giving me. For example, if I went along this branch right here, I could just put an equal sign here and say, well, that first flip was a heads, and then I flipped a tail, and then my third flip was a head. So this could be heads, tails, tails. This would be heads, heads, tails. This would be heads, heads, heads. This one would be tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And again, there are our 8 different outcomes here. Okay, so now I'm going to take this with me because we're going to use this to calculate some probabilities on the next part here. So let me just grab this. Okay, so it says if you were to flip a coin 3 times, calculate the following probabilities using our tree diagram here. Okay, so what's a probability that we get all heads? Heads, heads, heads. Well, that only happened in this one instance right here. And so that happened 1 out of 8 times. So there's the probability, 1 out of 8. If you want to talk about that as a percent or a decimal, by all means, go ahead. All right, what's next? What's the probability? Why can't I erase that? Oh, I guess I still took that from before. All right, what's the probability that we flip 1 head out of 3? Well, it depends on where that head came from, whether it was the first, the second, or the third flip, right? So if I look at all these different combinations here, here's an instance, here's an event where I only got 1 head, here's an event where I got 1 head, and here's an event where I got 1 head. So there were 3 possibilities out of 8 altogether of where I flipped 1 head. All right, next, the probability of no heads. All right, well, how many times out of these 8 did no heads at all come up? Well, just that one right there. So again, we're talking 1 out of 8 ends up being no heads. And the last part here, what's the probability that we get at least 1 head out of 3 flips? So at least 1 means we got 1 out of 3, or we get 2 out of 3, or we get 3 out of 3. Okay, so this could be the probability of 1 head, or, which means we're going to get to add here, because these will be disjoint events, 2 H's plus the probability that we get 3 H's. Well, those are 3 separate probabilities. Now we could do that, getting 1 head, well, that was 3/8. 2 heads, I could come up here and look at, well, there's 1, 2, 3 possibilities. So that's 3/8 plus 3/8. And in all 3 heads, that was that 1/8. So 3/8, 3/8, and 1/8 makes 7/8 altogether. And that is the final answer for D. But another way to look at this is to consider there are more events that we don't want to consider, or there's more events that we want than we don't want. Okay, there was only one event that we didn't want to see, and that was that we got 0 heads. Okay, and what's the probability that we get 0 heads? That was 1/8. So here's an alternative way of doing this problem and still getting the same answer of 7/8. We could say, all right, the probability of getting at least 1 head is 1 minus the probability that we get no heads, because that's, an event that we don't want to see happen. And the probability that we get no heads is 1/8. So 1 minus 1/8 makes 7/8 still. So again, you can use the addition rule for disjoint events, or you could use the complement rule, whatever way you feel most comfortable with. All right, up next. Now we get to discuss some probability rules. Now, we've already talked about these off and on. Our first rule we talked about was that any event is between 0 and 100%. The second rule we talked about is that the probability of all of our events combined make up our full 100%. And that S, again, was our sample space. Rule number 3 was the complement rule, where we said the probability of an event not occurring is just 1 minus the event or 1 minus the probability that that event does occur. And the fourth rule we talked about in class the other day, or no, this was still from the second video. The probability that A or B happens is the same thing as the sum of those individual events, as long as those 2 events are disjoint. And disjoint again meant that if one thing happens, the other thing cannot happen. So there is no overlap in a Venn diagram with disjoint events. The fifth rule we're going to discuss is when 2 events that can occur together. So they are non-disjoint, if you will. So consider flipping a coin 2 times. Let A represent the event that we get heads on the first flip, and B be the event that we get heads on the second flip. So what's the probability of event A that we get heads on the first flip? Well, that would be 1/2, right? 50-50. The probability of event B happening? Well, what's the probability that we get heads on the second flip of a coin? Well, that's also 50-50, 1/2. So what's the probability of events A and B? That we get heads on a first flip and we get heads on the second flip? Well, that ends up being 1/4, okay? Or 0.25 or 25%. This reasoning assumes that the second toss still has a probability of 50% of a head after knowing that the first toss was heads. When the outcome of the first event does not affect the probability of the second event occurring, we say the two events are independent. Okay? So just because we got a heads on the first flip doesn't mean that getting a head on the second flip happens any more or any less than it did on the first flip. Okay? Again, for example, think of, what if I flipped a coin 10 times and all 10 times I flipped tails? Then what's the probability that the 11th flip would also be a tails? Well, it's still 50%. Okay? It's not just because, just because I have this string of string of tails means that heads is due to come up. Well, if things are truly random, then they stay random and their probabilities stay exactly what they've always been. Okay? So we're going to talk about how to exactly calculate these independent probabilities. So two events A and B are independent if knowing that one event occurs does not change the probability that the other occurs. If A and B are independent, then the probability of A and B, and notice when we talked about disjoint events, let me hop back here, whenever we use the term or, then that meant that we were going to be adding our individual probabilities. And now notice the difference here. We're going to be using the term and. If we want event A and B to happen, then in the end we're going to end up multiplying those events. Okay, but we can only do this if A and B are really independent events. You have to be told that that is true in order to multiply the individual probabilities there. This is called the multiplication rule for independent events. So first, we're going to classify the following events as independent or dependent, and then we're also going to calculate their probabilities. So imagine we have a deck of cards and we want to draw an ace. We're going to put it back in the deck, shuffle the deck, and then draw another ace. Okay, so drawing the first ace and drawing the second ace, are those two events independent or are they dependent? Well, drawing the first ace has a 4 in 52 chance. There's 4 aces out of 52 cards altogether. So whenever I draw that ace, there's 3 left in the deck. But notice here, I said I'm going to put it back in and then reshuffle and then draw another ace. Well, what's the probability that I draw another ace when I put the first one back in? Well, there's still 4 out of 52 chances that I'm going to pull another ace because I could re-pull the same exact ace. Okay, the first time I could have pulled an ace of hearts, and the second time I could have pulled again the ace of hearts. So the probability of an ace and an ace ends up being a 1 in 169 chance. Now you might go, well, wait, how did you get 1 out of 169 when you have these two probabilities of 4 out of 52? Well, 4 out of 52 really simplifies to be 1 in 13. And since these two events are independent, then I may multiply together their probabilities. And 1 times 1 across the top is 1, and 13 times 13 across the bottom is 169. Okay? So number 3 here, it says draw a heart, shuffle, then draw a diamond. So I want to find what's the probability of getting a heart and a diamond. Well, first off, are these two events independent? So if I drew a heart, and then I shuffled the deck, and then picked another card. Well, what's the probability that I drew a heart? Well, there's 4 suits times 13 of each of those suits. So I have a 13 out of 52 chance of pulling a heart. But notice there's one little difference here compared here to the ace problem. I don't put the heart back, okay? So now is drawing a diamond 13 out of 52? It's not 13 out of 52. It's 13 out of, well, how many cards are left since I didn't put the original heart back? Well, now there's only 51. At this point, you can multiply these two things together, okay? So we can take 1/4, which is our 13 out of 52. That's where I'm getting this from, times 13 out of 51. So you can still multiply two events together as long as you take into consideration if events are really independent or not. So 1/4 times 13/51 makes 13 out of 204, simplified. Okay, so just because two events are not independent doesn't mean you can't calculate a probability. It just means that you cannot multiply together their individual probabilities. Again, I could not have taken 1/4 and multiplied it by another 4th because that probability for the second diamond, or for this diamond here, was not equal to a 4th because I didn't put the first heart back. If this said replace it, shuffle, and then draw a diamond, then it would be a fourth times a fourth, which is a 16th. So it is not uncommon for people to confuse the concepts of mutually exclusive events and independent events. Now, independent, we said earlier, was that the event of one outcome has no effect on the outcome of another event happening. Now, mutually exclusive means that if one event happens, then the other cannot happen. Now, you might go, well, that definition for mutually exclusive sounds pretty familiar, and it should, because it's the same thing as disjoint. Okay, mutually exclusive and disjoint are really the same things here. Now, if A and B are mutually exclusive, then they cannot be independent. And if A and B are independent, they cannot be disjoint or mutually exclusive. When do you use the rule for disjoint events? Is when we're adding probabilities, which means we need to see an OR. And when do we use the rule for independent events? Is when we want to multiply. And our key word here is and. So applying our probability rules here. First example, a transatlantic telephone cable contains repeaters at regular intervals to amplify the signal. If a repeater fails, it must be replaced by fishing the cable to the surface at great expense. Each repeater has probability of 0.999 of functioning without failure for 10 years. Repeaters fail independently of each other, which means that if one fails, that doesn't mean that the next one down the cable from it has a greater or lesser chance of failing. This assumption means that there are no common causes such as earthquakes that would affect several repeaters at once. So part A says, find the probability that 2 repeaters function properly for 10 years. So really we're finding the probability that we get 1 repeater that works and a second works. Well, can we just do the first repeater times the second repeater? Can I just multiply the individual probabilities? And I can only do that if the events are independent, which they told me in the problem above that they are. So what's the probability that the first one works? Well, 0.999. What's the probability that the second one works? The same thing, 0.999. So all I have to do is multiply those two probabilities, and there's my final answer. Let's do this instead. There we go. So really I'm taking 0.999 squared, which still puts me at a very high probability of 99.8% essentially. Find the probability that 10 repeaters function properly for 10 years. So we have the probability that the first works and a second repeater works and yada 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 and the 10th works. So there's really 10 things going on in here. And we can just set that equal to, again, that the first works times the second works times ... all the way up to the 10th works. So if you think about it, we're really taking 0.999 and we're multiplying it by itself 10 times. So we could just say that that's 0.999 to the 10th power. And that is equal to somewhere 0.99004. So we're still at 99% chance here that 10 repeaters will still work after 10 years. So part C, the last one here. The transatlantic cable has 300 repeaters. Find a probability that they all work properly for 10 years. Well, we can multiply the probability that the first one works times the probability that the second works all the way up to the 300th. So we're really taking 0.999 to the 300th power. And man, when you start getting many 0.999s and start multiplying them, they really start to work their way towards zero. Okay, so we're looking at a little over 74% chance that all 300 repeaters will be fine in a 10-year period. So we're looking at there's about a 26% chance that we're going to have to replace at least one at some point down the road. And one more example here. It says the letters of the word statistics are placed on index cards and thrown in a bag. List the sample space. Okay, so what letters could you pull out of this bag? Well, we don't want to include repeats. Okay, so we could pull out an S, we could pull out a T, an A, an I, and a C. Those are the only 5 unique letters that make up the word statistics. So our probability distribution, or our probability model that we talked about in the second video, here's all my 5 outcomes. And now what are the probabilities? Well, the probability of getting an S, well, there were how many S's in the word statistics? 1, 2, 3. Out of how many letters altogether? 4, 5, 6, 7, 8, 9, 10. So I have a 3 out of 10 chance, which is 0.3, 30%. Now what's the probability that I get a T? Well, there's 1, 2, 3 T's as well out of 10 letters, so 30% as well. A's, there's only one A out of 10, so 10%, 0.1. I's, there are 2, so 20%, 0.2. And C, there's only that one, so 0.1. And again, if I were to add all of my individual probabilities up to make my sample space, that should give me my 100% or 1. So last but not least here, let the event V that we have a vowel, and I would hope to goodness you guys know your vowels, right? A, E, I, O, U. We're not going to include Y here. And the event M is that the letter falls in the first half of the alphabet between A and M. So list the sample space for each and find the following probabilities. So for V, vowel, well, what letters up in our probability distribution or our probability model are vowels? Well, those would be A and I. What's the probability that we get a vowel in statistics? Well, we can just take our 2 separate events here and add them together. So 0.2 and 0.1 makes 0.3. M. What's the event M that we get a letter that falls in the first half of the alphabet between A and M? Well, S is not between A and M, and certainly T is not. A is, and I is, and C is. So A, I, and C represent our sample space for this event, and the probability would just be those 3 things all added together, because A, I, and C are all disjoint events. You know, there is no overlap between A and I. There is no overlap between I and C. They're individual unique letters. So 0.1, 0.2, and 0.1 makes our 0.4. V or M, that we have a vowel or it falls in the first half of the alphabet. Well, we can just really look at our 2 events here and see, well, what do they have in common? Well, not what they have in common. What do they have all together? Well, they have A's, they have I's, and there's a C. So A, I, and C would be vowel or in the first half of the alphabet. And that probability is, well, it's the same as what it was for just M, right? So it's still 0.4. This sample space is the same as this sample space, so the probabilities would be the same exact thing. And the last one here, M complement, that it doesn't fall in the first half of the alphabet. Well, those were our S and T's. So that is our sample space. And now what's the probability of that happening? We can add together the 0.3s, or we could come down here and take 1 minus the probability of that event. So 1 minus 0.4 gives us our 0.6 that we also get from 0.3 and 0.3. And that is all for the 4th video, and we will see you in the 5th video.